So here we're going to show the water ethanol binary again. We have another video where we looked at how water has a very sharp boiling temperature of 100 degrees centigrade. Here on the Kelvin scale, this would be equal to 373.15 kelvins. Those two things are equal. And then we had ethanol boiling at about 76 degrees centigrade. It's a little bit messy here. There's a minimum temperature and then it raises up. There's a so-called azeotrope. For our purposes, we're going to ignore all this stuff here. We don't care about the azeotrope just yet. So we're going to look at the experiments that somebody has done here and published in Wikipedia, and it shows a phase diagram, and it's going to be a little more quantitative than what we showed before. By the way, note the pressure here, 101.325 kilopascals is equal to 1 atmosphere. So somebody did all these experiments mixing ethanol and water together in various proportions from pure water over here to pure ethanol on that side. This would be the X sub E that we used in a prior video that we go from 0 to 1. They did all these experiments at a pressure of 1 atmosphere. So what they find out during their boiling experiments? Well, it looks like they did these experiments at fixed temperatures. So for example, notice that instead of a circle with a triangle directly above it, if we follow this circle here, we don't see a corresponding triangle there. So they didn't do these experiments at fixed composition. They were really aiming at fixed temperature. And so you can see that we can draw these horizontal lines that connect a circle to a triangle. What are the triangles? The triangles are showing the vapor composition. Remember, at any temperature above this upper curve, everything is a vapor. So this is the vapor state here. Everything below this lower curve down here, those temperature and composition combinations will represent things that are in a liquid state. And then in between those curves, we have liquid plus vapor. So we have this boiling interval here. Well, what they're doing is they're showing the compositions of the liquids and vapors that they get in an experiment. So if they heat up an ethanol water mixture and let it equilibrate at 366 degrees Kelvin, then they get a vapor over here that is much more rich in alcohol than the liquid that is left behind. So the liquid over here has, maybe about 5% alcohol or less, while over here the vapor is almost 30% alcohol. So it's much, much more enriched compared to the liquid. And this is true at any temperature. So we can come down to a lower temperature, 360 degrees. The absolute values have shifted, and we get a bigger difference between the liquid and the vapor composition, but the vapor composition is still enriched in alcohol. Here it's about 45% alcohol, compared to the liquid that's equilibrated with, which is a little bit less than 10% alcohol. So we have this huge difference in the vapor and liquid composition. This is the essence of what is happening in a distillery when we make whiskey or gin. We take a liquid and we boil it so that the vapor that we get is more alcohol rich than the liquid that's left behind. We capture that material, we capture that vapor, let it condense, and we can repeat the process. And if you look at a bottle of whiskey and it says double distilled or triple distilled, that means they've gone through this boiling process and vapor capture process a couple of different times. Anyway, the bottom line is that we can use a diagram like this to predict how the compositions will be related to one another. So you know that at 362 degrees, if you let that system equilibrate, you'll be able to have a vapor that has about 40% alcohol, and the liquid that's left behind will be something less than 10% alcohol.